Hello, good evening. Can you hear me? So, before we start, teka, ang dami pa nagjo-join. Okay, let's see. Alright, so good evening everyone. Thank you for joining us tonight on part 1 of our tropical design series. In this portion of the webinar, we're going to discuss the basics of tropical design, of course, which is climate, and an introduction of a topic that is not normally discussed when we talk about tropical design. So, to begin, what comes to mind when we talk about tropical design? A lot of things, of course. Number one, of course, for sure, somebody would say sun shading. Tropical design has been using shading devices to reduce direct solar radiation. Of course, we have verticals, horizontals, which keeps the building cooler and, of course, provide shade. When we talk about tropical design, do you imagine interior gardens, plant life inside the built environment? Basically, to not just to make it beautiful, but to cool the interior space through transpiration. Maybe it's about daylight, which allows natural light inside and lessens the need for electric lighting. Perhaps green roofs, of course, who could forget green roofs? When we talk about tropical design, everybody would probably use this one to reduce heat gain through incident solar radiation, especially on concrete roofs. So is tropical design something that is modern, or something that uses new technologies? Or maybe is it something that is using indigenous materials on modern designs? Or perhaps it's just the vernacular, the one we gotten used to, like the ones from up north, Ifugao, and even in Metro Manila. We have a lot of assumptions when it comes to tropical design, but to understand what tropical design is, we look first to its genealogy. Surprisingly, tropical design, the term itself came from their experiences in India in the 1940s. We all know that India was a British colony, and two major players, Maxwell Fry, a British architect, along with his wife, pioneered tropical building and town planning, as well as Otto Königsberger, an architect of Universal College London. He's a German who actually in World War II defected to the United States. His expertise was building physics. His father was actually a German scientist. These two people pioneered tropical design primarily in India when they tried to use modern designs and tried to build on the Indian climate. So basically, tropical design then became something that is coming from the modern perspective of architects. So they did government buildings, town planning, primarily in India. Okay, so tropical design essentially was part of a modernist movement. Both architects were part of this movement, similar to, of course, Farnsworth House of Mies van der Rohe, Alvar Aalto, even Le Corbusier. So, if we look back and try to define architecture, Fletcher in his book defined architecture as the result of influences in the geography, politics, technology, economics, and the society. This brings us to a very descriptive definition where modern architecture certainly becomes something that architects use with the advent of new materials and technology. So, tropical design is primarily used to achieve thermal comfort. If we go back again in India, it's a tropical savanna, so it's quite humid, it's hot, it rains. So the British are not used to that type of climate, so they try to build buildings and houses that they can actually live in. So they wanted to achieve thermal comfort in places that are that's very humid and very hot. So architecture now becomes a climate responsive and energy conservative design. So if we design now something that is climate responsive, low energy, and uses these strategies, we can now give a definition of tropical design as an application of climate responsive, low energy design strategies to achieve to achieve thermal comfort in the tropics. Using all of these techniques that we will be discussing further on in the series, you will have a realization that tropical design has been around us for quite a while, but it is because of man's need to be comfortable where they are. They try to be able to build structures that respond to the different climates around them. So after the term tropical design was coined in 1962, there was an environmental movement. This was the paradigm shift when people started to talk about architecture, the built environment, planning with respect to the natural environment. Essentially, it started in 1962 with the environment impact used in pesticides. And furthering on, in 1987, the term sustainability was used in the World Commission on Environment and Development. This was the first time sustainability was used. And then in 1992, the United Nations had a conference on environment and development at Rio de Janeiro. Agenda 21 used the word sustainable development. So it included all of the countries, including the Philippines. Okay. In 1993, LEED was established that had a goal to define green building by establishing common standards of measurement. And of course, in 1996, as response to Agenda 21, the Philippines created the Philippine Agenda, which had the same goals as the United Nations. Okay, and in 1998, green building was actually coined in a book. It was tackling different political, geopolitical, and environmental issues at that time. Okay, and in 2009, the Birdie program was established here in the Philippines by PhilGBC, which was incorporated in 2007. And then finally in 2015, the Philippine Green Building Code was promulgated here in the country. So the term tropical design came through a lot of changes through time. right now we call everything sustainable design, green building, everything. If you try to encompass everything, it's basically trying to design something with respect to its climate. So again, the definition would come back to the 1940s definition of a climate responsive and low energy design. Okay. So that handles for the genealogy. So I hope you have a certain overview of how the term tropical design came about. It's not a term that actually someone just dropped, and I've seen in most schools and universities it was never really tackled. Even in the most big universities, it was never discussed. But this is basically a short history of how tropical design came to be, and how it was used, and how it is continually evolving. Okay, so moving on. When we talk about climate responsive design, we need to understand first what is climate. In this series, we are going to discuss three things. Number one, we will try to define what climate is, and then we will try to look at the factors that affect climate, and then the third one would be defining the different climate zones and its characteristics. Okay. So what is climate? Okay. Climate came from the Greek word klima, which actually means slope or an incline. They were some scientists determined that it was actually a referral to the slope of the Earth from the equator to the pole. So even during those times, they already understood how the celestial geometry actually works. So the scientific definition of a climate is that it is a long-term average incidence of solar radiation, temperature, humidity, precipitation, atmospheric pressure, and the direction and speed of the winds and its geographical location. When we say long-term, it means that an average predictable atmospheric conditions over a period of 30 or more years. That is what climate actually is. So if you compare it to weather now becomes something that is interchangeable within the day. But climate is something that sticks with you for 30 or more years. So when we talk about climate change, that means the climate has changed in the last 30 or 50 years. So when we talk about the climate and its classification later on, you will understand why we try to gather data about the precipitation, the heat, the humidity to determine one's climate. Okay. So knowing the climate gives us an idea of how to design the building. So climate responsive design is integral to all green buildings. This is why we actually study climate. And as future architects, this will equip everyone with the knowledge and tools that when you can identify the climate, you can actually identify the strategies that you can do to respond to that climate and make better designs. So let's say, for example, you know the orientation, you know the wind, you know the amount of rainfall, you know the amount of humidity. You're able to design buildings that respond to those conditions efficiently, and therefore creating an actual green building. Okay? So what are the factors that affect climate? So there are a lot, basically, but we will try to group them into the major factors that affect the climate. Number one, of course, is the sun and earth relationship. Okay, this celestial relationship is probably hands down the greatest factor that affects our climate. If you've seen in science fiction movies, if the earth actually stops revolving, or if it goes out of orbit, a lot of things can happen in our atmosphere, in our magnetic field. So that is actually, well, to an extent, true. The relationship of the earth to the sun actually creates our climate. Okay, so the sun and earth relationship, showing you with this slide. So we have an orbit that is not actually circular. It's an ellipse. Okay, so during the aphelion, we are farthest away from the sun. During the perihelion, we are actually closest to the sun. And during March 21 and September 23, where the equinox happens, we are actually at equal distance to the sun. So the winter solstice and the summer solstice then gives us different distances from the sun, and therefore also gives us different amount of daylight during the day and different amount of evening during the longer evenings. So this sun and earth relationship gives us the different seasons that we have in the earth. But of course, in the Philippines, we only have two seasons. We have the wet and the dry. So looking at this diagram, I hope you can appreciate that it is not, number one, it is not the closeness of the planet to the sun that gives us that heat. Well, not really. But it's actually, as I will explain later, it's actually the tilt of the earth towards the sun. Okay, the earth is tilted about 23.5 degrees. Therefore, if you can see that line along the equator, it's not perpendicular to the sun. So when it revolves around it, it moves around its axis. We have different times of the day, and then when it revolves around the sun, we have different seasons happening all around us. Okay, so another view, looking at the Earth's tilt. I put there a tangent, surface tangent to the sun. Okay, so as you can see, the Tropic of Cancer is actually on this rotation is closer on the northern hemisphere to the sun, and to the right side, as you can see, the Tropic of Capricorn is closer to the sun. So that means it's more tangent. But again, it's not just the closeness that you are to the sun that you must appreciate that gives you the heat. Later on, it has something to do with the actual geometry. So looking at these two phases during the year, June 21 and December 21. June 21 is where the sun is most highest in our latitude, and on December 21, that is when the sun is much lower along the horizon. Okay, so the Earth's tilt also gives us the tropical belt. It's a belt. It's a continuous belt around the Earth. It's about 23.5 degrees north and 23.5 degrees south. This whole belt is where the most tropical countries are. So it shifts around when it revolves around the sun. the red axis that you can see is is the the imaginary center line, and then the tilt is where we actually rotate on the polar axis. So it's tilted 23.5 degrees. So it gives us here in Metro Manila a latitude of 14 degrees. So going back again, the the distance we are from the sun and the angle at which the sun hits us because of the tilt has something to do with the amount of solar radiation that is that's being absorbed by the earth. So let's take a look first. Solar radiations are basically electromagnetic fields. The visible light that we see is right there, almost in the middle. It's between 780 and 380. This light wave is the light that we see when you look at the window in the morning. Farther to the left of the spectrum, these are the infrared lights, and farther to the right are the ultraviolet lights. So basically, light travels in wavelengths. So this diagram shows you the apparent differences in the wavelength. So basically, the visible light spectrum wavelength is about the size of a protozoa, and the wavelength, the radio wavelength, is basically as big as humans and buildings. So this is just for you to appreciate what the different wavelengths of solar radiations are. Okay, so when we talk about solar radiation, we actually need to talk about the quality of the solar radiation. This is the light that we see. This is like sometimes it is what you also feel. The qualities of the solar radiation can be measured in 100 lumens per watt. This is the luminous efficacy of the sun. So the luminous efficacy is a measure of how well a light source produces visible light, and is the ratio of luminous flux to the power. So I would just want you to stop and appreciate that if there is daylight, there is actually heat. If there is light, there is actually heat. Light produces heat. Okay, I want you to absorb that first. And then we need to also know about the quantity of solar radiation. A while ago we were talking about the quality of light. This time we're talking about the quantity of solar radiation. So the solar constant, the amount of solar radiation coming from the sun, is about 1,395 watts per square meter. So if you can imagine a 60 watt bulb, if you've touched that before, that's just a small area. This one is 1,395 watts per square meter. That is the solar constant. That is the intensity of radiation reaching the upper surface of the atmosphere, and that solar constant may actually vary plus or minus 2%. We still have, that's why we have the atmosphere, that's why we don't burn. We have particles in the air, we have the clouds. So, but if you're above the atmosphere, you will actually be absorbing 1,395 watts of energy per square meter. Okay. So when the radiation heats the earth, it becomes surface radiation, but it can come in many forms. But before we discuss that, the amount of energy that reaches us is basically something to do with the surface incidence. It is actually governed by the Lambert cosine law. It states that the relative intensity of solar radiation or light on a surface is equal to the cosine of the angle of incidence and the relative area over which it is distributed. So basically, it's an inverse of this value. So if you can see the diagram here, okay. So if you're looking at the area B, which is the pink one, imagine the whole area of that rectangle. So the light of area B is hitting a surface that is perpendicular, perfectly perpendicular to itself. That is the area. But if you look at light C, it's basically a triangle, and the area is much bigger because the surface that it is hitting is not perpendicular to itself. So on the right hand diagram, if you see the circle light, the yellow circle, when I try to pass it through the vertical square, it actually touches the red area. But if I project it to the horizontal square, it projects an elliptical area which is much bigger than the red ellipse. So if the sun is hitting a surface at an angle, the amount of area or the energy is much greater than when it is hitting something that is perpendicular. So when the sun gives off the solar radiation and it hits the atmosphere, it actually travels through a straight line. So if you can see a line C to D, what can you see there? The sun is almost perpendicular. The line of the sun ray is almost perpendicular to line CD. So it is much shorter than line AB. So that means the light traveling from C to D is much faster than the light traveling from A to B. So the amount of radiation is reduced because the atmosphere absorbs some of those radiation. That is why when you're on the north or south pole, it is actually much colder. Okay, so there is a component called the solar altitude. This is just a basic chart. So as you go higher in altitude, the amount of intensity of solar radiation is actually higher. And if the angle of that altitude is more perpendicular, it's actually higher. So, for example, if you are at about 3,000 meters in altitude at about 90 degrees, the sun is hitting at 90 degrees, you will have about almost 1,200 watts per square meter of solar radiation on you. So the altitude actually is a factor as well in terms of solar radiation. Okay. So the duration of sunshine is also a factor. That is how many hours the sun is shining on a particular area on the earth. This is a graph showing, like, for example, in January. Okay, so we have about 11 hours of daylight, and on February a little bit higher. On about June 21, during the summer solstice, we have about 12 hours 59 minutes worth of sunlight. and then it goes down back again. Um, this is actually also the effect of the sun and earth relationship. Okay, so when the solar radiation hits the earth, it is sometimes reflected, it is sometimes absorbed, and it is sometimes it's also emitted back by the earth towards the atmosphere. It is called the thermal balance. If you remember your thermodynamics, this energy cannot be destroyed or created. It has to be recycled. So from one form to another. Okay. So the total solar radiation, let's say 100%. Okay. About 25% is absorbed into the atmosphere. So the farther away you are from the sun at an angle, the more solar radiation is absorbed by the atmosphere. Okay, and about 20% are reflected by clouds. Of course, clouds are also made up of water droplets, so it can actually reflect light. 5% is reflected from the ground. Once it hits the ground, it is reflected back. 27% is directed on the ground, and it is actually absorbed, about 20%. And 23% is diffused, meaning it hits the trees, it hits the buildings, it hits people before it is actually absorbed by the earth. So what happens to that energy? Once the earth receives that energy, it has to recycle it. It has to throw it back. So 20% is transformed into long wave radiation that is sent back into the atmosphere. 20% is being evaporated back into the atmosphere, and 10% is being returned as heat convection. So this is where you get the term greenhouse gases. So greenhouse gases in the atmosphere, such as the water vapor, carbon dioxide, absorb most of the Earth's emitted long wave. So the more water vapor and carbon dioxide you have in the atmosphere, the more that these things are actually absorbed and not returned back. That's why we have the greenhouse effect. So there's a cloud over us that absorbs the heat and does not let it go. Okay? So after you determine the amount of solar radiation, we now need to determine the winds. Winds are basically convection currents in the atmosphere, where the pattern of their movements are modified by the systematic differences in the Earth's land temperature, affecting pressure, and make significant patterns that persists over time. So these forces, okay, so we have distinct global wind patterns. So imagine this is the Earth, okay, near the equator, okay, we have the tropical front. That's basically the line, the equator. On north of it, we have the northeast trade winds, okay, and then we have a break. It's called the subtropic high, and then the wind changes direction, and then we have the westerlies. So the westerlies go to the right, the easterlies go to the left, and then there's another break, which is the subpolar front, before we have the polar winds again that goes to the opposite direction of the westerly. So just a diagram to show you. Now those breaks in the directions of the wind or the fronts is actually cells. So the heat from the sun is strongest at the equator, where the incidence of solar radiation is more intense. Okay. This means that the land and ocean ocean surface near the equator tends to be warmer than everywhere else. So that the heat from the sun that heats up the water drives the wind, drives the directions of the wind. Okay, so those breaks, they are actually cells. So the two cells north and south of the equator, they're called the Hadley cells. So the surface temperatures affect the temperature of the air above them, and because hotter air is less dense, so it goes up. It tends to rise, and cool air tends to sink. Okay, so that those are the properties of air. Rising warm air creates low pressure, and the sinking cool air creates high pressure. So when you here in the Philippines, when we turn on the TV and hear the news, you always hear the low pressure area, the intertropical convergence zone. You will always hear that because our country on the global scale, where we are at our latitude, is where these things actually are. So the winds that drive around the country are being driven by the intertropical convergence zones and the heat coming from the equator. Okay, so the Hadley cells, that's why this is the direction of the Hadley cells, and as the warm air rises up, it drives the air upward. So if you just look, you're looking where the tropics are, and then once it drives up, air cools down because of the cloud formations, because of the rain, and it drives down back again, and then as cool dry air, and then it goes back again due to evaporation. So these are the cycles that we have near the equator. So some air movements are the result of the systematic pressure gradients that rise from latitude changes on the Earth's surface and temperature. So because of the high and low pressure, it actually drives the air. Okay, and then because air is fluid like water, it's not actually clamped down on the surface of the Earth. It's floating on the atmosphere. When the Earth spins at its axis, what happens? The cloud actually is being left out. So this is the Coriolis effect. The Coriolis effect explains how a moving object seems to veer towards the right in the northern hemisphere and left in the southern hemisphere. So basically, if you're like the atmosphere is lighter, so it behaves like a fluid and held against the Earth's surface only by gravity and friction. So when the Earth rotates, the air lags behind the Earth. That creates the Coriolis effect. Okay, so the wind, the resultant trade wind, is the effect of the Coriolis force and the thermal force behind it. So this is actually also why the direction of the trade winds are all easterlies. Okay, so another diagram to show you the direction of the wind, the global wind patterns that we have on our planet. Okay, so around 30 degrees north and 30 degrees south, there are two bands of continually high barometric pressure. These are the descending winds. Winds in these zones are typically light and variable. But between 30 and 60 degrees north and south, however, there are strong westerly winds and prevail, blowing in the same direction as the Earth's rotation. So if you can imagine, if this is animated, you'll see how the differences in the direction the winds are, and how they change direction from the subtropic high to the westerlies to the polar high. Okay, so since the atmosphere is fluid. The annual wind shifts its direction. So in July, the solid line is actually the direction of the wind, and on January, this is actually the direction of the wind. So the wind doesn't travel on a straight line. That is why sometimes the tropical storms changes direction seemingly without pattern. So it's very hard to predict. On a continental scale, wind and weather are the result of the interaction between the global flow and patterns of regional pressure and temperature patterns created by the differences in the heating of the sun. So when the heat from the sun hits the water, hits the surface of the earth, hits the vegetation or even the mountain, it actually drives the wind into different directions. Okay. So just to touch on it briefly, hurricanes and typhoons are the same. It's the only difference is where they occur. They are all tropical cyclones. So if you are near the United States, in South America, let's say, what's that? Venezuela, you call these tropical cyclones hurricanes. If you are in the Philippines, you call it the typhoons. And if you're in Australia and somewhere in East Africa, you call it just cyclones. So these are all the same. They are the same phenomenon. They vary in force. They vary in direction, but they basically have their names changed because of where they occur. A tropical cyclone is the generic term used by meteorologists to describe this kind of phenomenon. Okay, so after wind, another factor that affects climate is the topography. When we say the topography, it is the mountains, it is the land mass, this is the amount of vegetation, etc. Okay, so topography greatly influences climate, as like mountain ranges, for example, can create barriers that alter wind directions, even the speed of the wind. It controls the amount of precipitation, its patterns, and hence the topographic features of the land can carry or channel wind in different directions. Excuse me. They can actually change the pressure while driving the wind, so it creates its own climate. Okay, so part of that is when we say precipitation, it's basically rainfall. Mountains play an important role in precipitation patterns because it basically drives the rain. So if you look at this photo, though, this is in the western United States. It's the Sierra Nevada. It's a good example. There's actually almost no moisture in the air, and this is the result of what we call the rain shadow. Rain shadow basically is if you see this diagram on your right side, imagine that's the Sierra Nevada mountains. Okay, so the wind coming from the ocean, let's say it's about 30 degrees. It's like the tropical climate. The mountain forces the wind to go upward. Okay, so as the wind goes up, it cools down. So from 30 degrees, about 1,000 meters up, it cools about 20 degrees, and another 1,000 meters up at 2,000 meters, it's about 15 degrees and it starts to rain. Okay, so the moisture coming from the ocean and the wind that drove it up creates rain already. So there's precipitation there, and continuously it drives up the mountain at 3,000 meters. It turns about 10 degrees Celsius. Okay, so at the apex of the mountain, it travels to the other side. Okay, and as the heat of the sun heats up the air, the cool air, it also increases in temperature, so the air goes down. Okay, so as the air is driven downward, it increases in temperature again, and the leeward side is where there is actually no rainfall. So the rain shadow is where the part of the topography of the land where the orographic lift occurs when the air mass is forced from a low elevation to a higher elevation. As the air mass gains altitude, it quickly cools down. Okay, and then at the other side where the rain shadow is, the air is actually heated up again. Okay? So it creates that shadow where there is no precipitation, and the wind is actually the temperature of the wind is much hotter than when it first came from the other side. Okay, so the rain shadow is basically the shadow of dryness that is left out, because the mountain, in its size, actually just blocked off all precipitation. Okay, so this is an example of that. On the on lower left hand side, you can see it's all green. This is Tibet. Okay, it's a plateau. Okay, from the windward side, it's all green. Okay, you can see it's really green, and then on the ridge where the white, the spots of white are actually snow. Okay, but on the other side, there's actually just brown color. It's barren. There's no moisture. This is where the rain shadow is on this location. So the mountain actually trapped all of the moisture and the clouds on the left hand side. Okay. So those are the major influences of climate, but those influences create elements. These elements are what you want to measure. So for example, from solar radiation, you want to measure temperature. Okay, the temperature, of course, is measured in Celsius. We are in the Philippines. We are using the metric system. So it's basically with the use of a thermometer. Okay, so when you get temperature, you just don't get one temperature. You get basically the average temperature over a week, sometimes the average within the day, and then the average of that throughout the year. You get the minimum, the maximum, you get the mean. As a broad description, monthly mean temperatures can be given for each of the 12 months. Okay, so because they are different. So if you're looking at this graph right now, you'll see that this weather data for Manila, it gives us the highest temperature that we have is actually in May, right? Okay, so here is another temperature plot. The red ones are the heating hours. They are about 27 to 38 degrees to 38. So these are the hottest hours during the day throughout the month. And the yellow line is the sunrise and the sunset. So during, let's say, 12 noon, which is about at here, on 12 noon, it's really hot. So 4 a.m., 2 a.m., 12 midnight, that's when you want to be outside. So these are only averages, of course. It can change, weather can change throughout the day. These are averages that we use to do scientific calculations. Okay, so the temperature is just one element. Another one is absolute humidity. Absolute humidity is the amount of moisture present in the air. It's in grams per cubic meter. These are the particles of droplets in the air. But relative humidity is much more useful. This is actually what you regularly feel. So sometimes when you feel it's hot, sometimes you say it's very humid today. This is the relative humidity that you feel. This is measured in the percentage. Basically, it's the potential and amount of moisture the air can hold at any given time. So that's why it's measured in percentage. Okay. So vapor pressure now becomes where the atmospheric pressure, P, is the sum of the partial pressure the dry air and the partial water vapor of the pressure. So vapor pressure is being it can be measured by barometers and other equipment. Okay, so these are examples of the dry bulb, relative humidity, and the vapor pressure. So to give an indication of the prevailing humidity, it is sufficient to establish the monthly mean. Okay, if getting the monthly mean of any type of element of climate gives you a lot to work with already. Especially for those who are going to do their thesis, you want to get these types of information through the websites of Pag-asa. Yeah, I will discuss some of them to you later. Okay, so precipitation, again, rain. So the collective term for rain, snow, hail, dew, whatever, it's precipitation. It's basically precipitated from the atmosphere. So it's something that came down from the atmosphere. So this is actually measured in the country, in the Philippines. Its rainfall is measured in millimeters. Okay, so this is the amount of rainfall in Manila. Let's say for in August, it's about 476.3 millimeters through average throughout the year. Okay? So that is collectively, it is measured by rain gauges. Pag-asa has this calibrated and they are all expressed in millimeters. Okay? So precipitation is the amount of moisture. Driving rain is what you see when you drive your car. It's the actual rain that hits you. Okay? So you also need to take note of this because in terms of architecture, it's used to express the amount of exposure that a building has in driving rain. So basically, if the annual rainfall or the average wind velocity, if you multiply them, it's basically the driving rain. So it's in square meters per second. So the amount of rainfall in an area multiplied divided by its the velocity of the wind, that gives you the driving rain. Okay, so if it's less than 3 square meters per second, you are considered sheltered. If it's between 3 square meters to 7 square meters per second, you are considered moderate. If it's greater than 7 square meters, then you have a severe driving rain. So you need to design around that. Sky conditions is very basic. It's the presence or absence of clouds, so you actually measure them as well. So on average, you get 2 observations during the day, and then you track the portion of the sky covered by the clouds, and it is expressed in percentage. So for example, when you say it's 100%, that means it's 100% covered by clouds. So it would look like this. Okay, so that's the sky coverage. So let's see here. On January, we have the greatest coverage. The total. Okay, we have the total from 10 to 90. That's the. And then we have in May, June, July, the shortest. Okay, so we have the highest coverage that we can get is almost 100, so we are very cloudy. And the lowest one is almost maybe about 5%. Okay, so we have in Manila we have a big range. Okay, this is how it looks like on 3D charts. Okay. So the 3D charts gives you the time of day and then the month and the amount of coverage we have on that particular hour. Okay, and then of course climate studies cannot be complete without the psychrometric chart. Psychrometric charts are tools for understanding the various parameters that we have discussed, like air, the temperature, humidity, precipitation in the air. Okay, so it looks like this, right? So on the succeeding parts of our study, we will be teaching you how to use this. This is a tool that you use to determine in many ways, in many aspects, when a particular element will either give off or absorb moisture. Okay, so just for appreciation, okay, it looks like this when you are actually working on it. Okay, so at the bottom you have the dry bulb temperatures. Okay, on the right hand side you have the dew point temperatures. These are the humidity, and on the top right hand corner, that's the relative humidity. Okay, the sloping, on the left side, that curve sloping up is basically your dew point. That if you pass that, it's going. If it's like, for example, you're measuring this outside. Okay, so at 10 degrees and about 0.05%, it's going to rain on a particular temperature. So if you pass that line, it's going to release off moisture. What is important here is when you plot the temperatures based on certain standards. Right now, most people are using the ASHRAE standard 55 that was established in 2004. That gives you the average comfortable temperature for you to be in for a particular work. In this case, if you can see the green dots, if you're designing a particular room, you want to be in that area of the graph. So basically, it's between 20 degrees and about 25-ish degrees. So this cyan box here on top of the blue one is where you want to be. This just basically shows you, it's very technical, it shows you where you want to be in terms of temperature and humidity. Because temperature is one thing. If you have higher humidity, you will feel that the temperature is even hotter than it actually is. Okay. when you just to give another example, when you hear on the news, they always tell you the heat index. The heat index is not the temperature around you. The heat index is actually the the function of humidity and the temperature within a particular area. So normally, if it's like let's say it's 25 degrees outside, it's practically cold for us, but the temperature is very high, and then the humidity is very high, of about maybe like 40%. So the 25-degree temperature becomes about 27 to 30 degrees already. So you feel that there's a certain amount of heat, and that is not the temperature, just actually the heat index. So that's the temperature and the humidity. So going back again to solar radiation, solar radiation is measured by a sunshine recorder. So it measures the sunshine, the radiation, in watts per square meter. So it's very important also to measure that, because that's the amount of radiation that is absorbed by any object on the face of the earth. So here again, on our graph for Manila, we have the graph incidence of solar radiation throughout the year. So it most look like will probably look like this. Okay. So for the purposes of detailed design, you want to have a typical day of each month for at least a year to have a good design data for whatever you're using. When we talk about solar radiation, this is when you try to calculate the cooling loads for your air conditioning system. So that's basically the heat that is transferred from outside of the building inward. Okay, so then we have wind, of course. Wind we measure by the velocity and the direction. So it's measured by anemometers. I think most probably you have seen one of these in control towers, especially in airports. Okay, so the only difference is that in urban areas you measure it at about 10 to 20 meters from the ground to avoid obstructions. But the velocities near the ground are a good deal lower than actually on higher elevations. Basically, as you go up, the velocities becomes higher than those that are on the ground. Okay, so when you graph those wind velocities and direction, you create a wind wheel. So the wind wheel basically tells you the direction of the wind, and then also the intensity of the wind, which is speed in meters per second. Okay. So this is an example again for Manila. East, we have the greater winds in the east. So the speed is about almost 22 meters per second. Eastward wind, about 20% during the day. So this is how you actually read them. Okay, so apart from all of those elements like the solar radiation, temperature, humidity, precipitation, rain, you also need to record special characteristics, or note down those characteristics that are in a danger or affects human comfort. Of course, when you're trying to design a building, it's basically for a person's use. So you want that person to be comfortable in that building. So you want to measure uh, whatever is whatever may affect your building in terms of human comfort. So practically, these are, the flooding, landslides, earthquakes, and what have you. All of these all of these information can be downloaded as a geohazard map. So the Philippines already has a database of them. You can all get them from the Mines and Geosciences Bureau, so you can download all of those maps. It tells you basically the landslide areas that we have in the country, where the flooding occurs. Sometimes you also have those maps that gives you the higher intensities of earthquakes, etc. Okay, so finally, you also have to record vegetation. Vegetation is very important because it's part of our natural environment, and vegetation is a function of climate. It influences what type of climate that we have, and vice versa. So basically, if you're in a tropical country, you have certain types of vegetation. When you're in an arid climate, you have zero vegetation, or some type of plant that grows with little to no moisture. So these are called biomes. Biomes are areas of the planet that can be classified according to the plants and animals that live in it. So climate can also be measured by the type of biomes, or plant life and animal life that exists in that area. Okay, so it's also an important element in the design of outdoor spaces. It provides shade and protection from glare. Okay, so we're on the third leg of this part. Now that we probably have that general overview of what climate is, and taking special note of precipitation and all of those elements that drive climate, we can now try to define the different climates that we have on the planet. This map is the Köppen-Geiger climate classification map. It depicts the world distribution of climates based on the classification originally invented by Vladimir Köppen in the 1900s. Okay, so basically, the way he classified this is through the amount of precipitation, the amount of dryness, and the amount of temperature that is present in a particular area. Okay, so there are several types of climates. Okay, so the first classification of climate is, of course, climate A, the tropical climates. It's found basically on unbroken belt around the Earth, near the 0-degree latitude or the equator. Okay, so they are mostly within the 15 degrees north and 15 degrees south. So the Philippines is in the 14-degree latitude, so we are actually part of tropical climates. Okay, so here, a characteristic of tropical climates is that the net solar radiation is very large. Okay, so the amount of solar radiation that is absorbed on that area is large and generally exceeds 18 degrees. Okay, so here in the Philippines, if we have a temperature lower than 18 degrees, we love it. But being in a tropical climate, generally the temperature is higher than 18 degrees. Okay. So type A climates are controlled mainly by seasonal fluctuations of the trade winds. So these are the intertropical convergence zones that I mentioned earlier. We have three types. We have the wet equatorial, which is type AF. We have the tropical monsoon, which is the climate AM, and the tropical wet dry, which is the type AW. So looking at it at the map, okay, all the blue spots are the tropical climates. The different shades of blue are the different types of tropical climates. Okay, so as you can see, they're all within the 15 degrees north and south of the equator in latitude. Okay. Okay. So just share it again. Okay, so type B climates are the arid and semi-arid climates that cover about a quarter of the Earth's land surface. So mostly they are between the 50 degrees north and 50 degrees south, but they are also found in the 15 to 30 degrees latitude hemispheres. They exhibit low precipitation, so very low rainfall, 0 to no rainfall. The temperature varies during the day, and of course also during the different seasons and throughout the year. The humidity is very high in some areas where there is water, because there are deserts near the water, but sometimes there are parts of these areas that are far away from the water, where there are clear skies and very intense solar radiation, and hence very low humidity. Okay? So type B climates have tropical and subtropical deserts. Okay, these are the climates that are near the water. They have mid-latitude steppes and tropical and subtropical steppes. Okay, so this diagram shows you where the arid deserts are. These are the BWH and the BWK. And this one shows you the semi-arid areas, which are also classifications of B. Okay, so basically they are the dry areas on the Earth. Okay. Next we have the type C climates. Okay, so type C climates are found throughout a major portion of the middle and high latitudes. Okay, this is about 25 degrees to 70 degrees north and south. So these climates have winter and summer seasons. So during the summer, the polar front in its jet stream moves poleward, so it moves up, and the air masses of tropical origin are able to extend to higher latitude. So the warm air from the tropics goes through climate C and D, and then is is pushed forward up to the poles, and it cools down again. So during the winter, as the circulation moves back to the equator, tropical air retreats, and the polar outbreaks influence the weather in this subtropical zone. So the sources of precipitation here are basically convections, mainly from the tropical air. So since if you remember the map earlier where the hurricanes and typhoons come from, here they don't have that, but they have convection. So the rain mostly comes from convections over land, from air coming from the tropics. Okay, so the three types of classifications are the humid subtropical, the Mediterranean climate, and then the marine west coastline climate. Okay, so this diagram here shows you the different type C climates that we have. Okay, so the humid continental climate, the type D, and the continental subarctic climate are here. Okay, so they are on the higher latitudes. All right, so type E climates, they're the last type. They are the polar climates. They are the climates 60 degrees north and south or higher. So basically they are the polar climates. Climates are characterized by low temperatures, low precipitation, but vary greatly in diversity. Okay, so they have tundra, and then they have snow and ice climate. So the snow and ice climate are the permafrost, so meaning it's always cold there. In this map, they are the gray ones, so the north and south poles. Okay, so I understand it's very confusing. So just to show you how it's classified. Okay, so this is just to show you how Köppen classified type A to E climates. On the first column, that's the type of climate that you have, so A, B, C, D, E. The second column is the subtype. So we have for type A climates, see here, for you to have a type A climate, you will have to have a temperature coolest in a month is 18 degrees or higher. If you have precipitation of at least 60 millimeters, you will be subtype F. If you have 60 but not greater than 100. So basically this is how you classify the climates, particularly through the amount of rain and the amount of temperature that is present in that area. So how does that affect us here in the Philippines? What is the Philippine climate? Okay. Philippine climate is characterized by relatively high temperature. As we said earlier, it has to be higher than 18 degrees. So we also have high humidity and very abundant rainfall. Okay, so in many aspects, we're very similar to Central America. And if you look at the map of the world, we're basically almost at the same latitudes. Okay, so in the Philippines, we have 5 climate types. Okay, so many of you might be surprised that we have a tropical rainforest, we have a tropical monsoon, We have tropical savanna, humid subtropical, and oceanic. So these subtypes are characterized by relatively high temperatures, oppressive humidity, and of course plenty of rainfall. That's why we only have two seasons, the dry and the wet. Okay, so if we use the Köppen-Geiger climate classification map, the Philippines now becomes something like this. Right? So if you're living somewhere in Baguio, you might have type C classification, and on the rest of the country you might have tropical classification. Okay. And if you see it there in Mindanao, on the higher elevations, you might have other type C climates. All right, so that ends our part 1. If you are looking for other references, these are the ones that we've been used in this discussion. So we'll probably make this available to you so you can track and read back